Assalamualaikum warahmatullahi wabarakatuh. We are from Group 1. Today, we will present about water supply system at Endau-Rompin National Park.
Now, this is the topic for our presentation today. Firstly, we have the project background. Project background will be covered in introduction, problem statement, objective and scope, equipment. Next, we have the project design and calculation. Project design and calculation, we cover the schematic design of the water delivery system and calculation. And third, we got the cost analysis. Fourth, conclusion. And lastly, we got the reference.
Okay, let's meet our team first. First is Afiq Daniel. Second is Wan Muhammad Ifan. Third is Nur Izzatul Najla. Lastly is me, Muhammad Azhan.
So the introduction for this proposal, basically Endau-Rompin National Park is located at the junction of the Johor and Pahang, and the park is currently offer basic services including lodging, a prayer hall and restroom. So these services requires a lot of water supply. A detailed analysis reveals that there are a need for an improved water delivery system due to the increasing visitor needs. So the main goal of this proposal is to fully satisfy the water supply requirement through a concept that combines modernity and sustainability. Hence, the proposal aims to preserve the natural purity of the park while enhancing the overall experience for visitors. So the problem statements. First is the insufficient water availability. Basically, Endau-Rompin Park have a abundance number of employees and visitors. So this lead to a lack sufficient access to clean, drinkable water due to the park limited water resources. Next is the environmental impact. Due to the limitation of water resources, the visitors and the employee transferring water from outside sources not only upsets the natural ecology but also increase carbon emission.
Okay, let's continue with the objective. The objective of this project is to prepare a proposal to supply water at Endau-Rompin National Park. The scope: to study the flow rate of water from the reservoir to the tank, to discover the total head loss in the system, to identify the efficiency of the pump to deliver the water in the pipeline, and lastly, to study the cavitation will occur or not on the system.
Next, I will proceed with the equipment. So the main thing in equipment is pipe. So it is used to supply the water from the river to the water tank and from the water tank to Lubuk Merikil, Lubuk Tapa and visitor complex for public use. It is available in variety of grades and material, but we decided to choose stainless steel. Although stainless steel is considered expensive, but it offers advantages such as it can be recycled to produce new items, hence the price is low, while the other items cannot be recycled. Next, it is also anti-corrosion. Due to its corrosion resistance, the pipes rarely rusted. And the last one is the durability, which is the ability to withstand pressure compared to other materials. The second equipment is water tank. We chose stainless steel as the material, and for the capacity, we decided to choose 24,000 liter as the capacity since it is distributed to the public use at National Park, and it also has advantages such as lower life cycle costs. Why it is said so? Because it has a longer lifespan and require less maintenance. And the second one is durability and longevity. Stainless steel's strength and its flexibility allows it to maintain its own structure even when there is environmental changes. Next, we use elbow 90-degree flange. This pipe fitting is important in piping as it can shift the direction of pipes by 90 degree. The quality, such as its corrosion resistance, is useful to joining and altering the direction of piping system. It also has advantages. So the advantages are cost-effective maintenance. It is the process of maintenance and replacement. For example, when there is a system maintenance or replacement due to component failure, we can detach the pipe fitting without opening the whole pipe. Next one is efficiency. It's properly placed fittings can decrease the friction losses in pipes, allowing the water to flow smoothly. The next one is T's branch flow punch. The function is to change the direction of flow from one pipe to another. It also can be used to connect different components or to change pipe size. It is usually located at the main branch of the pipe, and it also has advantages such as it saves time because it does not have to change direction at every distance, and it can be installed in a single operation without having to rotate any single equipment. We also put globe valve, which is fully open in this project. Globe valve is designed to regulate flow in partially open position. Its characteristic suits them well for control valve application, um, but and it also has its advantages such as good shut-off capabilities. It is easy to maintain, and it also can be used as a stop check valve in case the disc of the valve is not attached to the stem. Another important thing and in this project is the pump. Based on the calculation, the suitable pump to use is the centrifugal pump. Pump is used to convert the mechanical energy to hydraulic energy through force that is acting on the fluid. It creates rotation to create velocity in a liquid which turn into a flow. The advantages of centrifugal pump is corrosion resistance, as it can tolerate corrosive materials. Next, its energy efficiency. Centrifugal have the highest energy efficiency compared to other pumps.
Okay, let's continue with the project design. Preliminary design figure. This is the first design that we have discussed and sketched based on the site layout of Endau-Rompin National Park. We get the site layout on the internet. This national park get the water source from the river, which is Selai River. We use centrifugal pump to move water from the river to the water treatment. Then, the treated water will be transferred to the water tank, and the water in the tank will be transferred to the Lubuk Mareket, Visitor Complex, and Lubuk Tapoh using centrifugal pump. Okay, next is the final design figure. This is the design that has been improved based on the preliminary design figure. We have placed the detailed equipment used in the system on the design.
Now we move on into the calculation part. This is the calculation for the pipeline from the reservoir to the tank. We set the pipe diameter is 0.1 meter, and the area we use the area formula, and after we calculate we got the area of the pipe is 7.854 times 10 to the power of -3 m squared. Next we find the flow rate Q. We set the flow rate is 20,000 liter per 5 hour. So 20,000 liter is our capacity of the tank, and after we calculate we got the flow rate is 1.11 times 10 to the power of -3 meter cube per second. Next we find the velocity using the formula of Q equal to AV. After we rearrange the formula, we got V equal to Q over A, and to find the velocity, after we calculate we got our velocity is 0.1413 meter per second. Next, for the Reynolds number, we use the average temperature of water at 30 degrees C. From the table we got the kinematic viscosity nu at 30 degrees C equal to 8.009 times 10 to the power of -7 meter second meter cube meter squared per second. To calculate the Reynolds number, we use the formula of RE equal to VD divided by nu, and after we calculate, we got our Reynolds number is 17,642.65. This is more than 4,000. So our flow is the turbulent flow. Then we take the epsilon for the stainless steel, our equivalent roughness for the stainless steel, we use the epsilon equal to 0.3 millimeter. Then we convert it into the meter, we got 0.0003 meter. For the equivalent roughness, we use the formula of epsilon over d, and after we calculate, we got 0.003, and we take the red number and the equivalent roughness to the Moore's chart. Then we got our frictional factor equal to 0.0317. Next, after we got all that data, we calculate the head losses. For the HL measure, we use the formula of HL measure equal to FLV squared over 2GD. After we calculate, we got our HL measure is 0.042 meter. Next, for the HL minor, we use the formula of KLV squared over 2G. For the HL minor, our KL is elbow, 90 degree bend elbow, and we have 3 elbow in the pipeline, so we got 3 KL elbow, V squared over 2G. After we calculate all that, we got the HL minor is equal to 9.159 times 10 to the power of -4 meter. Next, we use the Bernoulli equation to find the head losses for the pump. After we simplify the Bernoulli equation, we got the equation is HP equal to V2 squared over 2G plus Z2 plus HL. After we calculate all that, we got our HP is equal to 2.55 meter. Next, we calculate for the pump output. For the power output for the pump, we use the formula of rho G HPQ. After we calculate, we got the power output for the pump is 27.77 horsepower. Next, for the power input for the pump, we also use the formula of rho G HPQ. But for the power input, our HP, we minus it with the head losses. So we neglect the head losses in the power input. And after we calculate, we got power input for the pump is 27.30 HP. Next, for the efficiency, to calculate the efficiency with the formula of P power input over power output times 100%. After we calculate, we got the efficiency for the pump is 98.31%. Next, we got the calculation to calculate the cavitation. Is it occur or not occur? We got the NPSHR from the developer is equal to 8 meter. And to calculate NPSHA, we use the formula of PATM over gamma plus Z1 minus HL minus PV over gamma. Our Z1 is 1 meter from the reservoir, and our L total from the reservoir to the pump is 2 meter. Our HL measure, we calculate, we got the 6.4517 times 10 to the power of -4 meter. Our HL minor, after we calculate, we got 3.0529 times 10 power of -4 meter. So after we calculate NPSHA using the formula above, we got our MPSHA equal to 10.90 meter. So our MPSHA is more than MPSHR, so the cavitation will not occur. Next, for the part 2 calculation for the pipe line from tank to the campsite. Also, same, our pipe diameter is 0.1 and our area is 7.854 times 10 power of negative 3 meter squared. Our flow rate, we set it into the 30 liter per day for all the 3 campsites. So we estimate that one campsite got 10 liter per day. So total of 3 campsites, we got 30 liter per day. After we convert it into the meter cube per second, we got 3.47 times 10 power of negative 4 meter cube per second. Next, we find the velocity, Q equal to AV. After we rearrange, we got V equal to Q over A. After we calculate, our velocity is equal to 0.0442 meter squared, 442 meter per second. Next, for the Reynolds number, also we take the average temperature of water is equal to 30 degrees Celsius. Then we look at table and we got our kinematic viscosity, nu equal at 30 degrees Celsius to 8.009 times 10 power of negative 7 meter squared per second. To calculate the Reynolds number, we use the formula of Vd over nu. After we calculate, we got our Reynolds number is 5520, 5520. It's more than 400, so our flow is turbulent flow. Next, our roughness for stainless steel, also same, 0.3 millimeter. And we convert it into the meter, we got 0.003 meter. Next, to find the equivalent roughness, we use the formula of epsilon over D. And after we calculate, we got our equivalent roughness is 0.003. After that, we take the equivalent roughness and the Reynolds number value, and we check for the Moore's chart to get the frictional factor, and we got our frictional factor is equal to 0.40. Next, we calculate the head losses. First, we calculate the HL major equal using the formula of HL major equal to FLV squared over 2GD. After we calculate, we got our HL major equal to 0.236 meter. Next, for the HL minor, we use the formula of KLV squared over 2G. In HL minor, we have the KL for the root valve and 2 KL for the T. And lastly, we got 2 KL for the elbow, 90 degree elbow. And T is branching, it is branch flow. And root valve is fully open. After we calculate all that, we got our HL minor equal to 1.255 times 10 power of negative 4 meter. Next, we got the Bernoulli equation, and after we simplify the Bernoulli equation, we got the equation to HP equal to V2 squared over 2G plus P2 over gamma plus HL. And to find the pressure, we assume that in the campsite have 40 houses with the 5 meter height. So we use the formula of pressure equal to rho GH, but we times it with 40 house. So we got the formula is 40 rho GH. So after we calculate, we got our pressure is 196 1,962,000 Pascal. After that, we take the pressure value and put it into our Bernoulli equation that have been simplified above, and we got our HP is equal to 200.24 meter. For the last part, we calculate the power output for the pump using the formula of rho GHPQ. After we calculate, we got our power output for the pump is 681.63 HP. Next, we calculate power input for the pump. And in the power input, we neglect the head losses. So we use the formula of rho GHPQ after we calculate and minus with the head losses. We got 680.81 HP. For the efficiency, we use the formula of power input over power output times 100%. And after we calculate, we got our efficiency for the pump is 99.89%. Next, for the last part, we want to calculate the cavitation. If it if is it occur or not. Uh, so for the MPSHR, we got for the developer of the pump is equal to 8 meter, and for the MPSHA, we use the formula of PATM over gamma plus V1 minus HL minus PV over gamma. So our Z1 is 0 because if there is no elevation at the pump, and our HL total is 1 meter from the tank to the pump, and our HL major equal to 0. Our HL major after we calculate we got 3.9830 times 10 power of negative 4 meter. Our HL minor is equal to 4.5383 times 10 power of negative 5 meter. So we take all the value and put it into the equation above for the MPSHA, and then after we calculate, we got our MPSHA equal to 9.90 meter. Which that our MPSHA value is more than MPSHR value, so the cavitation will not occur.
So after considering all the pipe used, the pump, the tank, the pipe fitting, we make an analysis for the cost of this project. So the pipe, the stainless steel pipe, which costs around 68 ringgit and 40 cents per meter. So the total estimated length cost, so the total estimated pipe cost is around 25,070 ringgit and 65 cents. Next is the pump. We use centrifugal pump, which costs normally 3,400. So we use 2 centrifugal pumps, so it will cost 6,800. Next is the stainless steel water tank, which costs RM 3,000. While for the pipe fitting, we have elbow 90-degree flange, we have T branch flow and globe valve. So the total cost for the pipe fitting is 6,089 ringgit and 80 cents. So the total estimated cost is around RM 40,960 ringgit and 45 cents.
So we have managed to design a water supply system at Endau-Rompin National Park. An efficient water supply system is essential not only to fulfill the user's need but also for the preservation of the national park's ecosystem. Through this project, it has enhanced our understanding in managing a water supply system at Endau-Rompin National Park. So, all the calculations needed in this project require our knowledge of fluid mechanics from calculating Reynolds number, major and minor losses, pump power, net positive suction head, which is NPSH, and Bernoulli equation. So, during our findings for the specification and material for each equipment, we also consider the cost because we try to minimize the cost so that it will be as cheap as possible for this project to be economical. So for the outcomes of this project, it allows us to make use of fluid mechanics to use it in our daily lives.
So this is the reference, all the reference that we use to make this report. We have 9 reference. So this is all the reference.